Okay, so next, Prim's algorithm. So implementing it is not very hard. Throughout, you're going to have a bit of a deja vu, which we will see soon why. So we start with an arbitrary vertex, let's say one is the start vertex, and then we have a set S of vertices. S, as long as it's not the whole set of vertices, we pick the vertex, we pick the edge of minimum cost from S that goes outside S, we add it to the tree, and we add it to S, and we repeat this process, right? This is exactly Prim algorithm. We always add the minimum cost edge across the current cut and move the vertex that we just connected to the other side of the cut, right? So number of iterations is linear, right? Because we have to occupy every vertex. Scanning all the edges takes off m time. So overall we get off n m time. But that's of course a very naive implementation. We can do much better, right? And the basic idea is that we're going to make the Dijkstra algorithm we make Prim's algorithm to look like Dijkstra's algorithm. And how can we do that? Well, think about it. Here we don't, instead of thinking about this edge, think about maintaining for every vertex outside S the cost of the cheapest edge connecting it back to the current set S. And think about it as the current distance. For every vertex there is the current distance to the set S, right? And so if we think about it like that, then we're going to have oops, what happened? I jumped forward somehow. Okay, so if we're going to do it like that, then we are going to have to, we're going to first have distances. So for every vertex there is the distance to the set S, which, and for every vertex we're also going to have P of V, which is going to be the vertex that it's coming from, the previous vertex, right? Okay, now we are picking the vertex. Instead of picking the vertex that, the edge that have minimum cost from the car to outside, we pick the vertex outside S that have minimum distance to it, and according to this array D, and then we find the edge from this vertex V that we decided to add, and we go to the vertex P of V, the vertex that it connected to S with, right? P of V must be in S, so this is an edge. We found V of cheapest cost. The cheapest cost is just the cost of this edge. This might be, this is P of V, right? And so we set the edge E is going to be VP of V. And now we add the edge to the spanning tree, and we add S to the vertex. And then we have to update this array D and P, right? Which we can again do by just, for example, scanning all the edges. That will not be an efficient way to do it, but we can do it. Okay, next step is to tighten the code a bit. Okay, so how would we tighten the code? Well, you know, this stuff is just rewriting the stuff. It's not really important, just writing it in a more compact way. But then, right, and the rest is very similar, right? So that's not really any big difference. So let's go on to the next step. So the next step is that I'm going to elaborate on how to update the distances, right? So how do we update the distances? You know, all those rewrites are just the same algorithm, right? It's just a different way to present it. Okay, so V is still chosen as the V with the minimum dV is just argmin of this, right? The vertex with minimum cost outside S. So this is fine. And now for the updating, we are just going to take new vertex that we just added, and clearly we need to update the prices only along the edges adjacent to it, just like we did in the extra. So for every edge that is adjacent to V, right, we see whether d of u, the distance of the vertex u to the set has changed. Well, what is its distance? It's either the current distance or the minimum or cost, or minimum with the cost of the new edge VU, right? If indeed we changed the distance, right, using the edge UV is now the better option, then we also need to update the previous vertex, the previous pointer, to say yes, we are coming from V, right? And that's it, right? So that's the new version of Prim's algorithm, and that should seem very similar to the extra, because in fact it is the extra up to a really minor change, right? So I put on the right the version of the extra. This is a version of the extra that together with the distances also output for every vector is a previous pointer, p pointer, such that, if you want to find the shortest path, not only the distance but also the shortest path, you travel back on this reverse tree, right? So the code looks identical. There is a difference whether S is picked arbitrarily, right? Here we picked arbitrarily. Here it was a parameter because we want a distance. So that's one difference. And the second difference is, of course, in this calculation. And this is literally the only difference, which is kind of amazing, right? So in the Prim case, the cost of a vertex, we looked on a new vertex that inserted to S, and we look on all the adjacent edges, and any adjacent edge, the cost was changed, either the minimum, the current cost, distance, or the cost of the edge. In the extra thing, we had to consider also the distance to V and add it to the cost of the edge, right? So that's the only difference, right? This is a term that is missing here in the left side, this plus thing, right? So it's literally the same algorithm. It's really the same algorithm except for this minor change, which is kind of awesome, right? Because same algorithm, same algorithms. And since they're essentially the same algorithm, we should be able to implement it in the same way, right? What do I mean by that? Well, the extra we implemented using priority queues and Fibonacci heaps and got better running time. So we should be able to do it with Prim, and indeed we can. It's completely straightforward. So we have a priority queue. We already went over that when we spoke about the extra, and we need, in fact, to use Fibonacci heap, where we can do the decrease key in constant time and extract mean cost as log n. And then when we use priority queue, the running time is becoming, we have off and extract min operation, right? Every time we do this in the loop, this happens n time. We have to do decrease key. That happens off m time because we are going to do a decrease key on an edge only once. And that's it, right? So as such, if we use a regular heap, we will get m plus n log n time, which is just the running time of Borovska's, and essentially also the running time of Kruskal, which we will see shortly. And using Fibonacci heaps, as we already saw for the extra, we get running time n log n plus n. So that's good. So we can implement Prim's algorithm as efficiently as the extra, and we are happy. It's a pretty efficient algorithm.